Hi, hello. Welcome back to our MP channel. Myself Rama Obrat, chemistry lecturer. In the previous video, we discussed about imperfections in solids or defects in solids. The imperfections of the solids are further classified into four types, but according to your syllabus, only two. One is point and another one is line defects. The point defect is very important according to your syllabus. The point defect means it is a defects or irregularity or deviation from ideal arrangement around a point or an atom in the crystalline substances. It's just simply around any one point or one particle there is a missing of a particle or any presence of extra particle and all that. So deviation is observed. It is point defects. The point defects are classified into three types. One is stoichiometric defect. Yes. Next, second one is non-stoichiometric defects. Third one is impurity defects. Stoichiometric defects. In the previous video, we discussed about stoichiometric defects. What are stoichiometric defects and what are the classification? Just recall yourself in your mind. What are the types of stoichiometric defects? There are four types. Just recall in your mind. Okay. The stoichiometric defects are classified based on the ionic and non-ionic type of particles. For non-ionic type of particles, that means atoms or molecule, these stoichiometric defects are two types: vacancy defect and interstitial defect. And for ionic type of ionic type of particles, for example, sodium chloride, zinc oxide, AgCl, KCl, for such type of crystal, the stoichiometric defects are two types. The two types of stoichiometric defects for ionic particles is Schottky defect and Frenkel defect. What is Schottky defect, and what is Frenkel defect, and how we can easily distinguish between Frenkel and Schottky and all the part we discussed in the previous video. In this video, we are going to study about non-stoichiometric defects and impurity defects. When you observe the old questions paper for your second year annual exam point of view, non-stoichiometric defect and impurity defects are not much important compared to stoichiometric defect. Okay, let us discuss about non-stoichiometric defects. The non-stoichiometric defects are further classified into two types. One is metal excess defect, another one is metal deficiency defect. So in this video, we are going to discuss about three types of defects. One is metal excess defect, another one metal deficiency defect, another one is impurity defects. The word metal excess and the metal deficiency itself says metal. Usually we are represent the metal in the form of M plus or M plus or M plus 2. Yes, that means these are positively charged. Metals means these are positively charged ions. So therefore metal excess, the point metal excess says that cation excess. Metal deficiency, cation deficiency. Understand the concept? So the cation deficiency word is explained in another way. The another way of explanation is metal deficiency, because metal means positively charged. That means cation. Metal excess, cation excess. Metal deficiency, cation deficiency. Metal excess defect. Can anybody guess how metal excess take place? Metal excess take place in two tabs. One, anion vacancy take place, automatically cation become excess. One. And another way, okay, just you can see it. Okay, metal excess defect taking place in two different way. The possible way of formation of metal excess defect is, one is metal excess defect due to anion vacancy. For example, in your class, there are 20 girls and 20 boys. When boys become excess, suppose there is a vacancy in the girls side. Suppose only 19 girls and 20 boys. Then, yes, boys excess take place due to vacancy in the girls side. And another possible way, there is a presence of extra boys. That means in a previously, that means pure crystal contains 20 boys and 20 girls, and after the defect there is a presence of extra cation, extra boys, then only excess take place. The boys excess take place in two different way. One is excess of boys or vacancy of the girls. Okay, similar way the metal excess defect take place in two different possibilities. The one possibility is metal excess defect due to anion vacancy. Another one is metal excess defect due to extra cation. Okay, let us go to the how metal excess defect take place, deficiency take place, and example and all that. The non-stoichiometric defect. The first type is metal uh, excess defect. Okay, before that, what is non-stoichiometric defect? Non-stoichiometric defect, defects in which disturb the stoichiometry of the compounds are called non-stoichiometric defects. What do you mean by this? Stoichiometry of the compound is disturbed. Stoichiometry of the compound disturbed means, non-stoichiometry means, in the previous video we discussed about the non-stoichiometric. Stoichiometry means correct. Non-stoichiometry means not correct. For example, one crystal contains 10 positively charged ion and 10 negatively charged ion. Okay, I'm consider 10 positive charged ion initially, 10 negatively charged ion. Then how much positive cation? 10 cation, 10 anions. Ratio is 1. After defect, suppose missing of one cation and one anion, the ratio become 1. In this case, or such type of defect, we are called it as only stoichiometric defect. Correct? It is known as stoichiometric defect. Electrical neutrality maintained. Simultaneously, positively charged ion and negatively charged ion remain same, or the ratio remains same. Such type of defect is stoichiometry. Then what do you mean by non-stoichiometry? Electrical neutrality should be maintained. That means how much positive charge is observed in the crystal, same type of negative charge. Charge may be from ion or it may be from electrons. There is a possibility. Okay, the charge is maintained by any other particles also. Therefore, in all the solids we observe the electrical neutrality. Electrical neutrality is maintained. But in case of non-stoichiometry, electrical neutrality maintained, the electrical neutrality is maintained by any other particle. For example, suppose it contains 10 positive charged ion. Metal crystal contains 10 positive charged ion and 10 negative charged ion. After the defect, 10 positive charged ion remains, 1 negative charged ion evaporated, and this negative charge is maintained by any other particle like electron. Electron contains one negative charge. This ion is evaporated, but electron remain or acquire the place of the negative. So total negative charge become 9 plus 1 electron, 10 negative charge, 10 positive charge. Electrical neutrality maintained. But what happened? 10 positive charged ion is there, but only 9 negative charged ion. Ratio, initially ratio is 1, 10 by 10, 1, but in this case 9 by 10. So disturbance in the ratio of the positive and negative charged ion. So what is the conclusion? Disturbance of the stoichiometry means disturb in the positive charged ion, number of positive charged ion and the negative charged ion in the crystal. The ratio when is disturbed, then it is disturbed in the stoichiometry. I think all of you clearly understand what is the meaning of disturb the stoichiometry. Okay, so correct means stoichiometry. Stoichiometry means correct. Balance means stoichiometry. Stoichiometry means balance. When positive charged ion and negative charged ions are balanced, then it is stoichiometry remains same. When it is disturbed, when number of positive charged ion, number of negative charged ion is different, then disturbance in the stoichiometry. Okay, next is these defects are either due to presence of metal excess or metal deficiency. Therefore, there are two types of non-stoichiometry defect. Okay, let us discuss about metal excess defect. The metal excess defect take place due to the two reason. Correct. One is anionic vacancy, and another one is, what is another possibility? Anion vacancy, metal excess take place due to cation excess. Okay, there are two type. One way, one is vacancy in the anion. So in this case, negative ion may be missing from their lattice site, leaving the hole. Hole means vacancy or uh, void. Leave the hole in which the electrons remains trapped or entrapped to maintain the electrical neutrality. Okay, just to you read the sentence once again. Not only once again, you can read 1,000 times, you can't understand clearly. Whenever we observe the uh, formation of metal excess defect in animation, then only we clearly understand the concept. Okay, in the next video we can next slide we can see the animation of metal excess defect due to anion vacancy. Okay, I'm consider the example of sodium chloride crystal. Okay, the positive charged sodium red sphere and the blue sphere, it is chloride ion. It is sodium chloride crystal. All the particles are orderly arranged, and this one is the three-dimensional view. Okay, this is the crystal, sodium chloride ionic crystal. In the sodium chloride ionic crystal, due to change in the temperature or the pressure or any other external energy, the weakly bonded negative charged ion, weakly bonded any one negative charged ion. Negative charged ion means chloride. In I'm consider the example of sodium chloride. Therefore, chloride is the negatively charged ion. Weakly bonded chloride. Why it is weakly bonded? One chloride bonded with 4 sodium. Correctly observe, one chloride attached to 4 sodium. But in actual formula, sodium chloride, one sodium, one chloride. But in this case, or in the crystal, actually, one sodium bonded to 4 chloride. There is a possibility of weakness of the one bond out of 4. So due to that change in the properties that affect the bond, and bond easily undergo cleavage, and one negative ion may be missing or evaporated. Okay, one next one chloride, yes, one chloride in this place, one chloride is evaporated, and the reason of the sodium chloride or the place become vacant. Okay, this place become vacant, but vacant place not remains as a vacant, the vacant place is acquired by evaporated chloride. Okay, when you observe, just observe the chlorine evaporation. Chlorine evaporated, not evaporated in the form of Cl, it evaporated in the form of Cl2, correct? Chlorine, whenever chlorine molecule form, then only evaporation take place. That means it should uh, leave its electron. Okay, chloride first, Cl minus. It is evaporated by leaving the electron. One electron is missing means it become Cl. Okay, 2 chloride from the big crystal. I am considering only one small portion. Okay, in the big crystal, 2 chloride is missing by leaving 2 electron, and it is evaporated in the form of Cl2. Yes, Cl2 is evaporated, or I am considering the smallest portion, therefore I am considered Cl minus. Cl minus evaporated by leaving its electron. Electron remain or acquire the place of chlorine, and this electron, how this electron remains in the vacant? Is there any reason? Yes, the reason of electron remains in this place because of this positive charged ion. This positive charged ion trapped the electron in this region. This region is named as F center. This region is known as F center. Then what do you mean by F center? F center means electron is trapped by positive charged ions in the metal excess defect. The center or the electronic region is known as F center. F stands for Farben center. Okay, Farben center means electrons trapped. And because of the identification, the name of the scientist as well as the Farben center place, due to that the word is introduced, it is F center. Okay, for your exam point of view, what is F center? There is a possibility of asking the question, what is F center and how F center is formed, and in which type of defect we observe the F center. Okay, metal excess defect due to anion vacancy. In that cases we observe the F center. Clear? Okay, we are going to discuss about the next thing. Next is metal excess, or okay, let us discuss about consequences of metal excess defect. Then there are 3 different consequences is observed. Consequences, what is the meaning of consequences? Consequences means what are the result of metal excess defect, or what are the uh, things we observed after the metal excess defect. Okay, one is the sodium chloride crystal impart yellow color in the flame. So this is due to metal excess defect. Similarly, potassium chloride impact lilac or violet color. Okay, next lithium chloride shows pink color. Okay, the reason of this coloring of the crystal or impact of color this is reason of the metal access defect. Okay, this thing is very important for your competitive exam. Please remember, sodium chloride shows yellow or impact yellow color, potassium chloride violet color, sodium lithium chloride pink color. Okay, so these are the things important for your competitive exams. There is a possibility of asking the question on this part. Okay, not only for your competitive, for your annual exam point of view also, this thing is very important. Okay, next, another type of metal excess possibility, the metal excess defect due to metal excess defect is due to presence of extra cation in the interstitial site. Okay, interstitial, what is interstitial site? Vacant site or holes or voids between the particles, the empty space between the particle. In the empty space, there is a presence of an extra cation. You already know that one thing, electrical neutrality should be maintained, no? So how this electrical neutrality is maintained? In the big crystal, suppose there is a positive, negative, positive, negative, positive, negative, positive, negative is there. The interstitial site is acquired by suppose positive charged ion. Then how electrical neutrality is maintained? The electrical neutrality is maintained by the another electron acquiring the neighboring interstitial site. The neighboring, very near interstitial site or vacant space is covered by electron. One positive charge is excess, extra cation, and one electron become excess. Totally positive and negative charge remain same. Correct? One positive increases, one negative increases. Electrical neutrality is maintained. But what happened? Positive charge ion is more, but it is not positive negative charge ion, it is electron. Okay, therefore stoichiometry is disturbed. Okay, so in this case also stoichiometry is disturbed. Okay, example for such type of metal excess defect is zinc oxide. Okay, so zinc oxide means Zn O. Okay, Zn O. Zinc oxide shows white color. It's in room temperature, or the very pure zinc oxide is white crystalline crystal. On heating, it loses its oxygen and turns to yellow. Okay, how it is? Just observe the video. So this is the zinc oxide crystal. When zinc oxide crystal is heated, okay, when you supply the heat to the zinc oxide, it turns yellow. Why? The oxygen in the zinc oxide evaporated. When oxygen evaporated, only zinc ion remains, Zn2 plus is remains, that and electron remains. That electron undergo excitation, therefore it look like yellow. When we remove the flame, it again take the oxygen from atmosphere, turns to white. Clearly observe the video. Okay, just it turns to yellow, and again when we remove the flame, it gives it gives white color. White color turns to yellow on heating, and again white after removing the flame. Okay, the in equation we discussed the mechanism of this change in the color. Okay, zinc oxide is white crystalline solid. You already observed it is. When it is heated, zinc oxide decomposes to Zn2 plus. Whatever the oxygen present in the ZnO, oxygen is evaporated, only Zn2 plus remains. It places the interstitial site. That Zn2 plus goes to interstitial site, and two electron take the neighboring site because of two oxygen evaporate, one oxygen evaporated, O2 minus. Okay, two electron remaining. That two electron neighboring acquire the neighboring site due to excitation of this electron. This two electron, it causes the change in the color, or it impact the color. Okay, Okay, this is the white zinc oxide, white crystalline. When it is heated, it happened when it is heated, it turns to yellow. Okay, it turns to yellow because it evaporate, or it leaves it sorry it gives the oxygen. When it is heated, oxygen evaporated, O2 half. Okay, an oxygen, nascent oxygen evaporated, and Zn becomes Zn2 plus. For the balancing purpose, what when Zn becomes Zn2 plus, only when it gives the 2 electron. Yes, 2 electron is evaporated or ejected. Zn2 plus goes to neighboring site, and 2 electron goes to another neighboring interstitial site. This 2 electron goes to excitation, come back to ground state by liberation of radiation that contains that shows the yellow color. Okay, so this one is very important. Please take the screenshot of this one. There is a possibility of asking the question, what happens, or give reason when zinc oxide is heated, it turns to yellow. Give correct reason with equation. Okay, equation and this one para is very important. Please take the screenshot of this slide. Okay, next we move on to the metal deficiency defect. Okay, the metal excess is one type, and in this type there is two possibility: anion vacancy, cation excess. We complete the metal excess defect by studying all these things. And the next is metal deficiency defect. Okay, metal deficiency, uh, there are many solid which are difficult to prepare in the stoichiometric composition. Means balancingly the preparation is very difficult. It contains less amount of the metal in compared to the stoichiometric proportion. A typical example is iron oxide. Okay, I'm taking the example of iron oxide. It concludes how metal deficiency take place. Okay, I'm consider the example of FeO. In FeO, Fe2 plus, O2 minus. Correct? The size of Fe is small compared to oxygen, or because of negative charge, oxygen is bigger size. Okay, next Fe2 plus. Okay, next O2 minus. So it is the crystal, iron oxide crystal. You already observed the metal oxide crystal, or just rusted iron. Okay, oxide form of iron. So in this crystal, all the ions are or all the metallic ions are arranged in this manner. But what happens in the defect, and how defect is caused? Defect is caused in such a way that iron shows there are two oxidation state. What are the two oxidation state of iron? One is iron plus 2 oxidation state, iron in plus 3 oxidation states. Correct? Okay, these are the two different oxidation state of irons. In defect, what happened? One Fe2 plus, or sorry, 3 Fe2 plus is replaced by 2 Fe3 plus. Clearly observe the crystal Fe2 plus. Okay, next FeO, FeO. Okay, FeO. I made a small mistake. It become O, then it is correct. After Fe, it should be O. Okay, I'm just erase these things, and again I draw the iron oxide crystal FeO, FeO, O, FeO, Fe, FeO, FeO. Okay, in this case it is plus 2 oxidation state. All are, just imagine, all the iron is in the plus 2 oxidation state. Okay, after defect what happens? 1 2 3 sorry, 1 Fe2 plus is evaporated, that means 2 plus 2 charge evaporated, another Fe evaporated, another Fe evaporated. Just imagine 3 Fe, that means plus 2 into 3, how much? Yes, it is 6 positive charges evaporated. This plus 3 charges, okay, 1 Fe evaporated, and the next one is evaporated. Fe is evaporated, Fe is evaporated, okay, this one Fe is evaporated, 3 Fe is evaporated, and to maintain the electrical neutrality, to maintain electrical neutrality, 3 Fe 2 plus is evaporated means plus 6 charge is evaporated. To maintain plus 6 charge, how much Fe3 plus is required? It contains plus 3 charge. Therefore, 2 is enough to maintain electrical neutrality. Okay, plus 2 make the when 2 Fe3 pluses are there, then it create plus 6 charge. So after defect, what happens? FeO is look like in this way: FeO, FeO, O, Fe. It is plus 2 charge. It is plus 2 charge. It is plus 3 charge. O, Fe. It is plus 3 charge. Fe, O remains vacant. Why? Why it is remains vacant? Initially, there are 3 Fes is evaporated, correct? Plus 3, 2 charged, plus 2 charged, 3 Fe is evaporated, and only plus 2 plus 3 charged 2 Fes acquire the place, and 1 become remain vacant. So in this case, what happened? Metal deficiency observed. Why? This is a vacant space. Vacant metal vacancy observed. Metal vacancy means cation vacancy. Metal deficiency, cation deficiency take place, but electrical neutrality or charge maintained. Okay, so this is the metal deficiency defect. Okay, the last thing is impurity defect. Come to the last point of the defects part. Okay, impurity defect, don't confuse with all, because very near to one another, the concept is very near to each other. Due to that, there is a confusion, there is a possibility of confusion. Okay, correctly understand the concept of the defects, then it become very easy to all are theoretical part. Last one is the impurity defect. Impurity defect is positive charged ions are missed or evaporated, that charge is maintained by higher charged ion. So whatever the what are the things we discussed in the last slide? The metal deficiency, the metal in the metal deficiency, okay, very important thing is there one, a metal deficiency defect is, okay, metal deficiency defect is observed only in case of the metal shows multiple oxidation state. Okay, it is important, multiple oxidation state. Okay, multiple oxidation state observed in case of, multiple oxidation state is observed in case of iron, copper, nickel. Okay, mainly we observed the defect, metal deficiency defect in these 3 metals. Okay, because it shows multiple oxidation state. In the similar manner, we observe the impurity defect, but in this case different ion take the place, or higher oxidation state ion is take place the vacant space caused by the cations. Okay, let us observe the impurity. I am consider sodium chloride crystal. Sodium chloride crystal shows impurity defect. Okay, how impurity defect observed in sodium chloride crystal. Just observe. Don't necessary to read all these things. Okay, when you see this crystal piece completely and observe the animation of the uh, impurity defect taking place in this crystal. Okay, how this defect is observed? It is pure sodium chloride crystal. Suppose during the formation of sodium chloride crystal, suppose any strontium chloride is present, in small amount of strontium chloride is present, then it causes the impurity defect. How this impurity defect is observed and how electrical neutrality is maintained? Okay, just clearly observe this animation. Initially, all are correct. Okay, there is no defect. After or due to presence of strontium chloride, 2 sodium is evaporated. Clearly observe, 2 sodium is evaporated from the crystal and this place become vacant. This is a vacant space. 2 vacant space is created. Correct? How much charge is evaporated? 2 sodium ion means 2 plus charge is evaporated. When electrical neutrality is maintained, 2 positive charge should be maintained. This 2 charge is maintained by strontium chloride. Strontium from strontium chloride. Strontium Sr 2 plus. 2 plus means 2 plus of sodium is maintained by 2 strontium. Okay, this vacant space is a vacant space. Vacant space is acquired by strontium chloride. So any one vacant space is acquired by strontium. I'm showing the strontium chloride take place this vacant space. Okay, it acquire the vacant space. Yes, it acquire this vacant space. How many vacant space remains? Suppose 2 sodium is evaporated, 1 vacant space is remains. Or how much strontium acquire? 1 strontium is acquired, 1 vacant remains. So there is a one relationship is formed. What is the relationship? Suppose 2 sodium is evaporated, 1 vacant remains, or 1 vacant remains means 2 sodium is evaporated. 1 vacant is remains, then 1 strontium chloride is acquire the vacant space. That means how many vacant spaces are present in the crystal, same number of strontium acquire the neighboring side in the sodium chloride crystal. Okay, that is the relation. Same number of vacant and the same number of strontium ion present in the crystal. Okay, this is the impurity. Why it is impurity? Extra foreign particle, okay, positive charged ion is missed or evaporated, that charge is maintained by higher charged ion. So higher charge or the different ion, foreign particle, foreign ion. Okay, so therefore it is impurity. Suppose the sodium shows multiple oxidation state, then sodium suppose Na2 plus is there, then it takes the Na2 plus takes this place and maintain the electrical neutrality, then it becomes the metal deficiency. So whatever you observed in iron and copper, okay, so in iron and copper the same thing is known as metal deficiency, but it happens in different ion, then it is impurity. Okay, there are small differences between vacant and impurity. Okay, thank you for watching this video, and please read all the things present concept in the defects, and all things are very important for knowledge purpose. For your exam point of view, Schottky defect, Frankel defect, metal excess defect, sodium chloride color, potassium chloride color, and lithium chloride color, and the another thing is zinc oxide turns yellow on heating. Okay, these concepts are very important. uh, Thank you once again. Please subscribe our channel, press the bell icon to get early notification.